Good morning, year 13s. How's it going, everybody? Great. Benzene part 2, the evidence for its structure. Okay, guys, if you can say hi on the chat, that would be amazing. Just lets me know that it's there. I know I'm just waiting for my chat. There's Wink. Okay, guys. There we go. I hate the echo. It's a nightmare in this room. The echo's not brilliant. Okay, right, and there's Winkit saying hello, which is awesome. So what I'm going to do is I'm going to switch up my camera scenario. I don't know how much I'm going to use this one. There we go. Hola. Right, so let's go for that, and then I'll switch over to this one. Share screen. There we go, and I'll get rid of my YouTube feed because I don't need that anymore now that I know the sound's working. So just a shout out for Dixon. When Dixon arrives, can you say hello on the chat? That'd be great. Right, okay, guys, I'll switch my tablet to tablet mode, and let's crack on. I also need to put my little fan on. There we go. Right, so last lesson we were talking about delocalized stability in benzene. And I didn't actually quite finish. It was actually a really nice lesson. I really enjoyed it, although I had to change my learning objectives. So understand aromatic stability. This idea of delocalized electrons occurring between carbon-carbon double bonds that are within a bond apart. Just to let you know, by the way, that the stability doesn't actually have to come from carbon-carbon double bonds. You can actually have electrons join the delocalized system from other atoms. That happens. We'll talk about that a little bit today. And then we talked about butene. Yeah, we talked about the butadienes, and we talked about how there was a slight difference between the enthalpies of hydrogenation between the two of them. And I didn't sum up the lesson. I then drew out this diagram of enthalpy versus the two compounds and showing the difference in stability. And I now need to kind of complete that diagram really for benzene. I then attempted to draw some funky pi orbital overlaps. I don't think I did a particularly good job, to be fair. It's not the easiest thing to do. Usually we'd be modeling this in class. So when we arrive back in school tomorrow, the first thing we're going to do is get out some molly-mod kits, and we'll be able to build these molecules, and we can actually add in delocalized pi systems in these things to show where they're actually having this sideways overlap. So you've got your sigma bond, which is your head-on overlap between orbitals, s orbitals most of the time, and then you've got your pi bonds, which are your sideways overlap. I can't quite do that. Oh, can't just about. Sideways overlap of p orbitals, and that of course has an overlap above and below, whereas the head-on has only got a single overlap. And we'll talk about the strengths of these and the impact this has on the structure of benzene in a second, but I do just want to finish off. I'm going to create another lesson because I always think it's worthwhile me keeping a good track in my notes of all things. So this is structure of benzene part 2. So this is A2 benzene part 2. And we're looking at the evidence for the structure. Evidence for structure. So, because it's a rather unusual structure, and I get to give you a bit of a history of this from a guy called Kekulé. He's the guy that actually determined benzene structure with the help of a lot of help from Manchester University. Actually, it was a massive, the physics department at Manchester University provided an awful lot of his data to prove its structure being so odd. So our learning objectives, which I believe I copied, so if I just paste those in, that didn't work at all. Well done, Mr. Duncan, that was excellent. No! Oh, it's okay, it's all right. I can fix this. Let's get rid of that. It's not what I wanted. Delete. So, okay, my learning objectives, if I go edit, I can pull them out of there. There we go. Copy. And then close that down. Back over to here. Go paste. There we go. So those are my learning objectives for today. So 4 learning objectives. One is know the evidence for the structure. So they're going to do this. They'll give you a long answer question where they'll say, give the evidence for the odd structure of benzene, or why the Kekulé structure is incorrect. Number 2 is to understand its planar configuration. And then I'm going to make a link to other things with double bonds here, guys. That's actually really important. The planar configuration, and then that is going to be, I'm going to link that to other molecules. Yeah, link to others. Yeah, to other families. Actually, more other homologous series. To other homologous series. Yeah, the main one, of course, being things like aldehydes, ketones. They're a key one. Next one, understand bond lengths. Can I just point out that understand, I feel like, is a bit of a stretch. But it's more like to know your bond lengths, really. But it's nice to have a bit of a chat about it. And then number 4 is know benzene and the bromine water test. Okay, so the first thing we need to do is write down the evidence. So we realize that there are 2 structures, two common diagrams. So our 2 common diagrams for benzene are Kekulé, which is this one. This is Kekulé's structure. This is called the Kekulé structure. Yeah, and if you are asked, and this comes up a lot, if you're asked to name this, yes, if you're asked to name it, it is cyclohexane. That's the one that everyone misses. 1,3,5-triene. Yeah, it is not benzene. Please, please do. Everyone calls this benzene, and it's not. Yeah, structure number 2, the versus, of course, is now benzene. Yeah, with this picture. Yeah, so this is now benzene structure. That is now called benzene, and you can't name that any other way. Yeah, benzene is, of course, technically a common name, because you can't really name that because there's no it's saying that, you know, that the double bonds are delocalized. Just to also mention that sometimes I'm actually going to add another one in here as well, because every now and again in the exams they often draw this. Yeah, and I'm going to mention resonance at this point. Yeah, the Kekulé structure, when he first started putting the evidence together, this is what he actually drew as part of his paper. Sorry, I'm struggling to do a decent hexagon here. And what you realize is that the bonds have actually moved. They're moving around in a circle. Yeah. So this is called resonance. I wish they were the same size. That's going to really bug me. That I can adjust that, I think. Yeah, that's better. I'm happy with that now. So this is called a resonance structure. Resonance structure. And it's basically, the word resonance means to flip between the 2. So these 2 structures are actually, what you can imagine is, and I know this seems odd. Oh, hi, Dixon. It's good to see you, man. I'll mark you in on the register as soon as I can. So students often at this point say to me, well, hang on, Mr. Duncan. Why is it that we have 2 pictures for benzene? Why can't we simply discard Kekulé? Because it seems like a bit of a waste of time. You're telling us the majority of the time that this is the incorrect picture. So why are you bothering to continue to teach it? Well, the reason for that is because it's needed further on. So when we start looking at the reactions of benzene, you actually require the Kekulé structure to be able to predict products from reactions. So it's actually still needed. This is not something we can get rid of. We still need it to understand what's called directed substitution. Yeah, this structure, this is a note. So nota bene, NB. The Kekulé structure is still needed to explain directed, change my color if I can, to explain directed substitution. Directed substitution. Now, just to explain what this means, substitution, I'll do more of this at later on when we're doing reactions of this. What directed substitution means is that if you have benzene and you attach stuff, if you have a benzene ring like this and you attach items to it. So for example, I'm going to attach a chlorine to this. So if I now take that and I add on another group, let's say I'm going to add on another chlorine, yeah? What directed substitution means is that it's going to go in a particular location. Mute. Right, how's that, guys? Is that any better? Your audio is static. How does that sound? Is that any better, guys? Let me know if the audio is any better at that stage. I'll wait a second. There's no point in me continuing with the notes. At this point, just wait for somebody to provide a little bit of feedback. Yep, it's good. Okay, thanks, Fab. So what I was saying is directed substitution means that that chlorine here, this chlorine, will go into one of these three positions. Yeah, and it will go there every single time, and that requires Kekulé to explain it. We'll be doing that. We'll be doing that when we're doing the reactions of benzene. So that's something we will see later notes. We will come back to that. In the meantime, okay, so what's the evidence for benzene being this? This is where we now need to get into my learning objectives. So what is the evidence? Evidence for benzene. And that's actually the correct sentence. Yeah, it is the evidence for benzene, or the evidence for it not to be cyclohexo-1,3,5-triene. So what is the evidence for it being benzene? So first piece of evidence. So evidence. It's like a subtitle. Underline my subtitle. First piece of evidence is, so when benzene was first of all extracted from crude oil. Yeah, it was actually discovered just flat out in crude oil. And it was distilled off as one of the products during fractional distillation. And of course, when they were creating these liquids, so benzene, by the way, is a yellowish liquid. See if I can find you a picture of it. It is also horrendously carcinogenic. It's like ranked number 3 up there in the world. It's like one of the most carcinogenic compounds in the world. So benzene liquid. So it's almost colored. There you go, yellow liquid. There we go. It's not that yellow, by the way. Yeah, it's almost colorless from my understanding. It'll be an impurity that's making it really yellow like that. Yeah, let's see. I wonder what it actually describes it as. There you go. How to make benzene liquid. It's almost colorless. Toxic is a toxic flammable liquid. Let's just have a quick look at this. It's nice for me to get, I know it is, there you go, colorless liquid. Yeah, sweet odor, sweet and aromatic. No, it's a nightmare. They're even using that in the description. It's really annoying. So first thing that I think we need to write down is, so before I write down number 1. Sorry, I apologize. No, you can keep the number 1. You can do this as a nota bene. It's absolutely fine. So nota bene, another one. I love my nota benes. These are important notes, by the way. I'm not doing them for no reason. So number 1, so nota bene, bullet point, colorless liquid. Colorless liquid at room temperature. It is also extremely toxic and carcinogenic. Extremely toxic. But the key one that comes up in the exam is extremely carcinogenic. Now I want to carcinogenic, causes cancer. You can add that in if you want the translation for carcinogenic. That literally translates to cancer causing. Cancer causing. There we go. And I'll put that in a bubble. Okay. And it comes from crude oil. By the way, benzene is one of the major reasons why when you work on the oil rigs, because they're digging up raw crude from the ground, it contains benzene. So their risk of cancer increases. So that's why they get paid a vast sum of money to work on the rigs, because you're increasing your cancer levels. So, okay. So now we've picked up that nota bene. I'm tempted to show you the symbol for carcinogenic. You probably know it. Let's just quickly do carcinogenic. Symbol. Just wanted to show you this. It is kind of important. They've used it in an exam. There you go. Yeah, the carcinogenic symbol is this one. It's rather odd, to be fair. Yeah, so make a note of that the symbol has this like star in the chest. And they've done many in the past. They've used the toxic one before, but that one has appeared several times in an exam, and a couple of students were left standing having not recognized the picture. I don't know how they actually managed that. I don't know whether or not they missed this lesson of mine during the year, but they certainly didn't get it. So something to bear in mind. Okay, so pieces of evidence for benzene being odd. So number 1, so when benzene was first extracted from crude oil, so benzene was extracted. So by the way, this is me just doing a little bit of history in here, and the history is nice. Yeah, benzene, of course, was extracted as a colorless liquid, and it had a formula C6H6. Now, that is a very, very strange formula. Yeah, it's very, very odd. That's it. By the way, this is the molecular, the actual number of atoms of each element in a compound. This is the molecular, yeah, and then the empirical just being CH. Yeah, EMP form. Yeah, and of course, the first person who discovered this was a guy called Kekulé. Now, he started doing the analysis on this, and when he got the formulae, he started trying to draw pictures. So the first picture that he drew was this one. He did 6 carbon atoms in a row. And he added in the double bonds as necessary to give him the right number of hydrogens, which is this. So the first thing he drew was this. I'll do that spaced out. There we go. First thing he drew was that. And he named it, of course. Absolutely fine to name it. It doesn't show geometrical isomerism. So because this middle bond is going to rotate, of course. Yeah, but this was the first one he drew. So this is going to be hexa. Yeah, I'm underlining the A to remind you. Hexa 1, 2, 4, 5. Hexa 1, 2, 4, 5. Tetra. Now, I think the A goes in, although I think actually it doesn't. It probably goes tetrene, because tetraene is, I don't know. Let's check that. I think they'd probably allow it with or without this A, but it's probably going to be, it'll be probably tetraene. I'll go for tetraene. It doesn't flow that badly. But that's what he originally drew. Let's check that out. Let's Google it. So this is hexa 1, 2, 4, 5 tetraene. There we go. The A is still there. 1, 2, 4, 5 hexatetraene. Tetraene, yeah, it is there. I'm right. Hexatetraene. There we go. So this was the first thing he drew. Now, what he then, of course, did was he wanted to prove that this is the correct structure. So step number 1, test for the double bonds. So the first thing he will do, evidence number 1, is he tested benzene with bromine water. So the evidence was, and surprise, surprise, no reaction. So the first piece of evidence was there is no reaction with bromine water. Now that's weird. If it was an ene, it would react. What that tells us is that benzene is much more stable than a standard alkene. We know that alkenes like to reach out. Yeah, we did this. So the bromine water test, if you take an alkene, I'm just going to put R's on these. It doesn't really matter. Yeah, and we do bromine water, which is this. Now, bromine water itself, the molecule bromine is non-polar, but it is polarized on collision. But polarized on collision, re-emphasizing this from a previous lesson, on collision due to electron dense double bond, C double bond. Yeah, and then the double bond reaches out, the bromine breaks, we get our intermediate. Now what we're doing is this is electrophilic addition at this point. Yeah, we've got an electrophile. Here's our role of that is the electrophile. And we're adding to the alkene. And then the final step in the process is that one. There we go. And so alkenes usually decolorize bromine water. And this is because alkenes are relatively unstable. And they're electron dense and they want to break open. But benzene doesn't. So let's now do our graph for benzene on here. So this is so we've got down here, we've got cyclohexane. Cyclohexane. This is cyclohexane. So what we're now going to do is we're going to look at various people that could exist. So the first one that would exist would be, let's do cyclohexene. I'm going to run out of space, aren't I? Cyclohexene. And the difference between these two, everyone in this class should remember. So I'm going to ask this to Tenzi. Tenzi, what's the difference in enthalpy between these two, please? Can you remember from last lesson? What's the enthalpy change? It is definitely exothermic. It's coming down. What's the one for cyclohexene? The next shelf, I should try and color coordinate this. No, it's going to be tricky, isn't it? I've also made the benzene ring a bit too big for me to do the next one. It'll just about work. Well done. Thank you, Tenzi, minus 120 kilojoules per mole. Good man. Thank you so much. Then we're going to do, cyclohexa 1,4-diene. So notice 1, 2, 3, 4. Yeah, so they're not, so at this point, we have no delocalization because the double bonds are too far apart. Yeah, we know that these double bonds here, are separated by a carbon in the gap. Then they're too far apart. No delocalization. So if I now said to wing kit, what will be, this is a nightmare, can't rub that out. There we go. If I said, I'm going to get rid of the numbers as well, don't need those. So if I said to wing kit, what's the enthalpy going to be changed for there, please? He'll know the answer, I know he will. No delocalization, wing kit. On a glass of water. Well done, thank you very much. That's going to be minus 240, spot on. There's two double bonds, going to be doubled. So at this point, we then introduce benzene, and it's that we would expect our expected enthalpy change for benzene. Our expected was minus 360. Yeah, we expected minus 360 kilojoules per mole expected. But it turns out it's not. Benzene actually sits at 218. It actually sits at 218 about, this is where it's a bit of a nightmare for me to add into the picture because I should just, if I just move all these numbers here, I can add it into the diagram. Benzene sits at about there, actual 218. It's way more. This was minus 360. This was minus 240. This was minus 120. And benzene is actually minus 218. So it's way out of sync. We have a delocalized pi system between 3 double bonds. Not just, I know when we did the butene, the butadiene, when we had this guy, the expected for this guy was 240, and so this was the expected, and actually it was about minus 220. The difference is only small. Yeah, there's only a small discrepancy. But because benzene has 3 of them, and in a circle, it actually stabilizes it even more. So it's way, way lower. And at this point, since the reaction, because this is so much more stable, increased stability, increased delocalized stability, delocalized stab. Yeah, it no longer reacts with bromine water. It's not reactive enough to do it. Now that brings me to my second piece of evidence, which we've now just covered, number 2. The enthalpy for hydrogenation is much lower than expected. Much lower than expected. So expected, and these guys, you're probably wondering why I'm writing these down so much. You have to know these numbers. Minus 360 kilojoules per mole expected. Yeah, 3 double bonds, 3 CC double bonds. Yeah, actual 218, minus 218. I actually want to check that. It's been a while since I looked that up. Lol. I'm going to have to check that. I've said that saying, you've got to know the numbers. And I'm like, really cute. Yeah, don't. So let's do enthalpy of hydrogenation. Is it going to be in there? No. Hydrogenation. It'll be there you go, of benzene. Come on, 218. Come on. Damn it, it's 208. It's 208. Sorry, guys. 208. I knew it had a 2 and an 8 in it. 208. Apologies. I am human. Keeping those kind of numbers in my head is tricky. So it's actually 208. Minus 208. So what that means is the extra level of stability. So we can actually now calculate the increased stability. How cool is that? Increased stability would simply be the expected enthalpy minus the other enthalpy, minus the actual. Gives me what? So minus 360, minus brackets, minus 208, close brackets. So it has an increased stability of 152 kilojoules per mole. That there, this here, is the heat energy of stability. Shouldn't really do that. It's the difference in heat energy between the two, and that's the amount of energy and the extra stability it's providing. Would I want to do it as a positive? No, I don't think I would. That's interesting, isn't it? Now that I've Googled it, it'll be interesting to look at What do they often do on these diagrams? Delocalized energy, 150.7. There you go. Delocalized energy of benzene. Okay. 150.7. So anyway, so that's the delocalized energy, delocalized stability energy. Heat energy of delocalized stability. The heat energy of delocalized stability. That's what I would call it. Stability. Okay. Right, third piece of evidence, number 3. Now, the next piece of evidence is really cool. So I talked about, I was mentioning the history of this and how, this is what Kekulé drew. He had this colorless liquid, and he then went and made a visit to Manchester University. Now, Manchester University were doing cutting-edge research into what's called X-ray crystallography. Now, X-ray crystallography is designed to be able to see molecules at a molecular level. Benzene X-ray diffraction. There we go. And check it, it's beautiful. Look at that. Isn't it pretty? So what they did was they were doing these really cool things. There's laser diffraction, by the way, and then electron diffraction, X-ray diffraction, loads of really cool ones. But the key thing was, so when Kekulé turned up with this colorless liquid and said, right, the formula is C6H6, and I'd like to have a look at what shape it is, because I think it's a straight line, but it's not reacting with bromine water. They were like, no worries, we'll do that. So X-ray crystallography. So X-ray crystallography told them immediately that it was, and at this point we can add in the picture, why not? And it's evidence. Let's take that one. I quite like that picture. If it'll let me. Come on, laptop. Copy image. The X-ray crystallography told them a whole load of really important things. Told them 2 things, in fact. Okay, it's not letting me do that. Let's try it with my mouse. Paste. Come on. Huh. Uh-oh. I think my notes may have crashed. Let's close it and reopen it. Paste, there we go. So the X-ray crystallography told them 2 things. Number 1, X-ray told them it was a ring. So the first thing it did was it highlighted them very clearly that this was a ring. How cool is that? Look at that. It's a ring. I don't know quite why it's doing that. It's really weird. I've never seen that before. It's a ring. However, that wasn't the piece of evidence. So why did he not do that in the first place? Why would you wink it? If you get a liquid out of crude oil, in order to do X-ray crystallography, wink it, you need specialized equipment and specialized people trained to do it. You have to actually turn the liquid into a perfect crystal. It's really difficult. And it was only when it didn't behave the way that he expected on his chemical test with bromine that he realized that he needed to go and look at the structure further. Like, you wouldn't bother. Why would you? If it behaved the way that you expected in chemical test, you'd assume you were right. It wasn't until the bromine water thing threw a problem that he was like, oh, that's odd. And the hydrogenation was odd. So now at this point, guys, I need to tell you that there's a piece of evidence here that I need you to write down. And the first thing is, it told him X-ray crystallography, all bond lengths were the same. Now that's really weird. It also told them it's a ring, ring system, but this is not one that you give. Do not quote this in your exam. Not in exam. The evidence is in the bond lengths. Now, the reason for this is because a carbon-carbon double bond and a carbon-carbon single bonds have different lengths. The carbon-carbon single bond is 154 nanometers. The carbon-carbon double bond is 132 nanometers. I need to check my numbers, I'm sorry. But benzene was weird. It was an in-between. So let's go for bond lengths. Oh, are they there? Oh, sorry, do apologize. They're not nanometers, they're picometers. So a carbon-carbon single bond is 139, according to that. Really? Carbon-carbon single bond is 139. No, that's in benzene. Oh, yeah. So that's 139. Yeah, picometers. Apologize, not nano. Are they sure? 154. I need to check my numbers. The internet is a great resource, but let's say carbon bond lengths. I need these values. They're very important. Angstroms. Don't want them in angstroms, really. Prefer them in nanometers if I can. Let's try that one. So it's giving me a nightmare numbers. Don't like it. Single bonds, 154 picometers. Right. 154, that's correct, but it is picometers. 154 picometers. Next, the double bonds are 134. Okay. So these ones are 134 picometers. So based on this knowledge, the expected shape of benzene was this. I'll draw it like the Superman symbol. I like the Superman symbol. This was what was expected. Too long. This was what was expected. The Superman symbol. Because we've got short doubles, yeah, and long singles. However, benzene doesn't do that. Yeah, benzene is equal length all the way round. They're all the same. All of them are identical. And the length of that bond is an intermediate bond length, which is super weird. Benzene, now the great thing is I don't need to bother with the carbon-carbon because all the same. So benzene bond length. And the answer is 139. And they're all the same. Yeah, so these are 139. It is somewhere, don't get me wrong, it's closer to a double, but it is not a double. It's an in-between bond length. It's really strange. And they were the same all the way round, which meant it's not a system which contains doubles and singles. Because if it was and it was rotating, you'd probably hit a perfect average. The picture then became that guy. Really important. So all lengths were the same. Sorry, you need a note to bene, and its value is in between a CC double and CC single. And that's the end of the evidence for benzene. Now, at this point, I have now covered in my learning objective all the evidence, the bond lengths, yeah, benzene and bromine water. I just now need to cover, I know I've only got 3 minutes left in my lesson, but just to talk about the planar configuration. So whenever you have, planar, the word planar in chemistry means flat. Yeah, that's what it translates to, flat. And benzene is indeed a flat structure. I'm trying to draw it so you can see that, you know, the rings, like, and then you got the pies, the electrons in the delocalized ring, and above and below it. I'm trying to draw it 3D as best I can. There we go. And it's a flat system, and the hydrogens are coming out flat as well. Yeah, these are also flat. The whole structure of benzene is flat. Whole thing is flat, like a pancake. I want to put the ring in the center as well. So benzene is flat. So whenever you have a double bond, I want to show you this in relation to others. Yeah. So if you have something like an aldehyde group, as soon as you realize you've got a double bond system, this part here, it tells you that the molecule will be flat around that part. Yeah, the reason being is, and I can try and draw this a little bit better, the reason being is you have a sigma overlap to that H, you've got a sigma overlap to that R, yeah, but then we have a sigma overlap to the O, but we also have a delocalized pi system. The carbon has, I'll do it in a different color, the carbon has, oh, I'm going to have to make it bigger, carbon has its P, and the oxygen has its P. And that flattens it off, yeah? You can see this in other structures as well. So a great example is propene. I always like propene. We draw propene, of course, a lot of the time like this. But in reality, it's got some really funky structures. Because as soon as you see the double bond, you recognize that this part here will be planar, along with him, 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 and him. They're going to be in the plane. So we can draw that better. We can draw the carbons there, and this is going to be flat. Yeah, and that's going to disappear into the background. You can actually do this with our 3D shapes, by the way, guys. Yeah, that's going into the background. That's going into the background. This is one of the wedges, and that's got a H on it. And then this is a wedge, being the C there. And then this is tetrahedral. This is tetrahedral, this one. Like that. And the delocalized pi system means it's flat. It's flat around this structure. Anything surrounding the double bond means that anybody within that structure there is going to be planar. Because the pi system requires the side-on overlap both above and below. That's why. So because the p orbital splits off, it's because the p orbital is this, yeah? And in order to have sideways overlap, yeah, you realize it's got to have it on both sides. This is an entire py, and it's going to link it that way, and it will flatten out the rest of the molecule. Okay, so it's nice to talk about its planar structure. I do want to also mention bond angles. I think you probably get all these. It's not particularly difficult because they're flat. Yeah, it's 120 inside it. I'll do some more on bond angles next time. I do realize that my lesson's come to an end. So I will bring this lesson to a close. I hope you found it useful, guys. Thanks for hanging around until the end. I know that we're meant to be in your next lesson, so you guys can shoot off, and I will see you all very soon. Ciao for now.